In this part of the videos, we are trying to take a deeper look into the principles behind Huckel's rule and whether a molecule is aromatic or not. In the first part of the videos, we just basically learned the rules to decide whether a molecule is aromatic or not. And now we're trying to understand why those rules work. And we've already, I think, made some progress in understanding those rules. And there's really just one major topic left, which is we'd like to understand the 4n plus 2 rule. We'd like to understand why aromatic molecules have 4n plus 2 pi electrons. So let's get into that explanation. Now, the explanation is based on molecular orbital theory. Molecular orbital theory. We're going to use molecular orbitals to understand Huckel's rule. As I said when I started this deeper look, you don't have to watch this part of the videos if all you want to know is to know how to use Huckel's rule. You can use Huckel's rule without using molecular orbital theory. We're just trying to get a deeper understanding of why Huckel's rule works. So why should you watch this part of the videos? Well, maybe if you're just interested, or maybe understanding the rules will help you to use them. Also, finally, if you're in a rigorous OChem class, you probably have to know something about molecular orbitals. So seeing how we use molecular orbitals to understand Huckel's rule might help you to understand how to use molecular orbitals in general. All right, I'm going to be assuming right now that you have heard of molecular orbitals and that you know a little bit, or at least have seen a few examples of how they're used. I'm not assuming that you're an expert or that you feel comfortable with molecular orbitals or that you can get molecular orbital questions right, but I am assuming that you have at least heard of them and have heard of the basic concepts. If you've never heard of molecular orbitals at all before, I'm probably going to be going through this material a little too fast for you to understand what I'm saying. But if you've heard of the basic concepts, even if you don't have complete understanding of them, I think that the explanations we're going to go through will make sense to you. Okay, so let's start thinking about the molecular orbitals. Now, in order to understand Huckel's rule, remember that we don't care about all the electrons, we only care about the pi electrons. Well, as a result of that, in this part of the videos, we don't care about all of the molecular orbitals of the molecule. All we care about are the pi molecular orbitals. So in this whole section of the videos, we're just going to talk about pi molecular orbitals, not sigma molecular orbitals. So first of all, what are pi molecular orbitals? What are pi molecular orbitals? Well, the pi molecular orbitals are formed from the side-to-side overlap of 2 or more p orbitals. Pi molecular orbitals are formed by side-to-side overlap of 2 or more p orbitals. Here's our definition of pi molecular orbitals. The pi molecular orbitals are the orbitals that are formed by the side-to-side overlap of 2 or more p atomic orbitals. And this definition shouldn't surprise you very much because it's consistent with what we said before. Remember that earlier we saw that the Greek letter pi was the Greek letter for P. Pi is the Greek letter for P. You can kind of see a trace of that because if we spell out the word pi, it starts with the letter P. So Greek is the letter, pi is the letter for P. So it's not surprised that p molecular orbitals are formed out of p atomic orbitals. Hopefully this makes it a little bit clearer what the difference is between p and pi. P refers to the atomic orbitals, and pi refers to the molecular orbitals. So if you're just looking at a single orbital on a single atom, you would be referring to a p atomic orbital. But if you're referring to an orbital that is spread over the molecule, you'd be referring to the pi molecular orbitals. Now, like I said, there are other types of molecular orbitals besides the pi molecular orbitals. There's also the sigma molecular orbitals. There's pi and sigma. I'm not going to write it on the board, but the sigma molecular orbitals are formed from head-to-head overlap of atomic orbitals. Sigma orbitals are formed from a head-to-head overlap of atomic orbitals, but the pi molecular orbitals are formed by side-to-side overlap of 2 or more p orbitals. Let's also mention the principle of conservation of orbitals. Conservation of orbitals. Remember that the molecular orbitals are formed by combining atomic orbitals. Well, how many molecular orbitals do we get out? That's going to be a very important principle for us. How many molecular orbitals do we get out? Well, the number of molecular orbitals you get out is equal to the number of atomic orbitals that you're mixing. That's what conservation means. If you're mixing 2 atomic orbitals, you get 2 molecular orbitals out. If you're mixing 3 atomic orbitals, you get 3 molecular orbitals out. If you're mixing 4 atomic orbitals, you get 4 molecular orbitals out. Now remember that the pi molecular orbitals come from the overlap of p atomic orbitals. So if you have side-to-side overlap of 2 p orbitals, then you get 2 pi molecular orbitals. If you have side-to-side overlap of 3 p atomic orbitals, then you get 3 pi molecular orbitals. If we have 4 p orbitals overlapping, then we would get 4 pi molecular orbitals. We'll see some examples of that in a moment. Now, when we use the word pi, that can refer to either the molecular orbitals or it can refer to the electrons. What do we mean by the pi electrons? Well, obviously, the pi electrons are the electrons that are in the pi molecular orbitals. So if you know where the pi molecular orbitals are, you also know what the pi electrons are. The pi electrons are the electrons in the pi molecular orbitals. Now, earlier in the beginning of the videos, we already gave a definition of pi electrons. What was our definition of pi electrons? Remember that we said that the pi electrons are the electrons in side-to-side overlapping p orbitals. Earlier in the videos, we'd already said that pi electrons are the electrons in the side-to-side overlapping p orbitals. Well, you can see that's completely consistent with what we're saying right now, because the side-to-side overlapping p orbitals form the pi molecular orbitals. So again, the pi electrons are the electrons in these side-to-side overlapping p orbitals, which means that they're in the pi molecular orbitals. Here we have a molecule of ethylene, or more commonly acetylene. Let's try to write out the pi molecular orbitals of this molecule. Again, our goal is to write the pi molecular orbitals of this molecule. If you already learned about molecular orbitals, maybe you can do that on your own. So you might want to pause the tape and try to write down the pi molecular orbitals of this molecule. Well, remember that the pi molecular orbitals come from the overlap of the p orbitals. So we have to find some p orbitals to overlap. Well, we know that this carbon is sp2 hybridized, so it has 1 p orbital. And we know that this carbon is sp2 hybridized, so it also has a p orbital. So we have 2 p orbitals total. So how many pi molecular orbitals are we going to get out? Well, we use the conservation of orbitals idea that I was just talking about. Since we're combining 2 p orbitals, we should get 2 pi orbitals out. So I'm going to write down 2 levels. Here's the 2 energy levels. This level represents one of the molecular orbitals, and this level represents the other, pi molecular orbital. Since we put in 2 p orbitals, we get 2 pi molecular orbitals out. And we can actually draw what the molecular orbitals look like if you've reviewed this topic before. You might remember that the lowest energy molecular orbital should have all bonding interactions, and the top molecular orbital should have anti-bonding interactions. So we can actually show what the orientations of the p orbitals are as they overlap to form the various molecular orbitals. You might also have learned in your class that we would call this a bonding orbital and this an anti-bonding orbital. And oftentimes we use an asterisk to indicate the anti-bonding orbitals. However, in these videos, I'm not going to talk very much, or actually I'm not going to talk at all anymore about the orientation of the p orbitals that overlap to form the molecular orbitals. I'm not going to talk anymore about bonding and anti-bonding either, because we don't really need those concepts to understand Huckel's rule. All we need to know is how many molecular orbitals there are and what their energy levels are. So when we write the molecular orbital diagrams, all we're going to bother doing is writing the energy levels. What would be the energy level diagram for acetylene? Well, if all we care about is writing the energy levels of the pi molecular orbitals, all we have to do is just write two dashes. This dash represents the low energy pi molecular orbital, and this dash represents the high energy pi molecular orbital. So again, for the rest of these videos, we won't bother actually showing the lobes of the p orbitals. We're not going to identify bonding and anti-bonding because those tools are really not necessary for our understanding of Huckel's rule. What we do need to know is how many molecular orbitals there are, and very important, we need to know what their energy levels are. For example, here, this is the lower energy, and this is the higher energy level. So I'll erase this diagram because, like I said, we don't need this much detail to understand Huckel's rule.